Hello everybody, welcome to this remote presentation. My name is Florian Dörfler from ETH Zurich, and I will talk about online feedback optimization with application to power systems. This work has been mainly driven by my two collaborators, Adrian Hauswirth and Saverio Bolognani, and recently some PhD students joined our efforts, namely Lucas, Irina, Miguel, and Verena. I also want to acknowledge my postdoc collaborator, Professor Gabriela Hook, and our sponsors. Let me start off by shining a spotlight on the two canonical decision-making architectures that you're all familiar with, namely feedback and feedforward, or for the purpose of this talk, let's call them control and optimization. In feedforward optimization, you can arrive at a very complex decision, taking very complex specification into account. It could be optimal, constraint, multivariable, and so on. On the other hand, this relies on strong requirements. Namely, what you need is a set to optimize over in a very precise model, typically full state information, an estimate of any sort of disturbance hitting the system, and it's computational intensive. On the other hand, feedback control relies on very simple feedback policies, which are often just size or transfer functions, definitely so optimal and constraint. On the other hand, thanks to the forgiving nature of feedback, this type of decision making is very robust to any sort of model uncertainty and disturbances. It's driven by measurements and results in a very fast and agile response. So we observed that these two layers have almost complementary pros and cons, and often the complementary benefits are merged via timescale separation of combined architecture that is offline. You run the optimization in feedforward fashion that provides the set points to the online real-time feedback controllers. Let me illustrate how this works out and some caveats on an example that I take from power systems, and I will use power system examples throughout this presentation. Namely, I use the power system balancing example. So the quintessential task for power system is to balance load and generation. And if they're not balanced, so if there's more load than generation, what you see is an offset in the AC frequency systems. In this case, it will be operating below the nominal 50 Hz frequency. And the purpose of online control, that is indicated in this diagram here, springs and dampers, is to rebalance system based on frequency measurement. So we have these two decision layers. That is offline, we dispatch generation based, of course, on prices of generation, but also based on forecasts of loads and renewables. Okay, we don't know those ahead of time. Online, we'll then have to mitigate any sort of uncertainty and fluctuation through feedback control, essentially some PI control based on frequency to rebalance the scale. It turns out in power system, the separate offline and online decision layers are not enough. What we have to do on top of that, we need to have a man in the middle. Essentially, we need to reschedule a set point every once in a while whenever the uncertainty was too large, our forecast errors were too large, and we had any sort of disturbances that materialize. And the online controls cannot keep up with all of this fluctuation and uncertainty. In this case, you have to redispatch generation, activate reserve generation, or even shed load in the worst case. As you can imagine, as we incorporate and integrate more and more renewables in the grid, we only see more uncertainty, more fluctuation, more disturbances, and thus we probably will also observe more and more of these rescheduling actions. Let's take my home country, Germany, for example, where here I plotted the data. How much do these rescheduling actions cost in millions of euros? So the costs are huge, as you can see, and they're more and more increasing, right, as we increase more and more renewables. And thus the conclusion we should draw is that this architecture of separating offline optimization and online feedback control becomes increasingly inefficient, definitely, and may even become infeasible as we have more and more uncertainty in generation. So this sort of conclusion can be found throughout power systems, not only for this balance example, also for other power system ancillary services. You typically have separate decision layers that all hit their limits under increasing uncertainty. Similar conclusions can be drawn, a similar case can be made for examples from process control systems or any sort of queuing, routing, infrastructure networks. In all of these examples, you typically have separate layers, and these layers hit the limits under increasing uncertainty and thus need some sort of cross-layer decision making. And different architectures have been proposed in different communities. What I'd like to explore today is a particular type of block diagram, which is the following. On the right-hand side here, you have the physical system driven by disturbances and control actions. And on the left-hand side, you have the controller. I take now a particular controller, namely what I use is an optimization algorithm, but not a regular one. I use an open algorithm that has inputs and outputs, and online algorithms. So it's not a batch optimization, but it's recursive, can deal with streaming data. And I real-time interconnect this algorithm as a feedback control of the dynamical system. In the simplest case, you may think about such an algorithm as just take a gradient of an objective function that depends not only on the decision, but also on the measurements you take. So that's the open part of the algorithm. You real-time interconnect the algorithm to physics, possibly having some sort of saturation or projection effects here to take constraints into account. Okay, and all of this runs online. And you hope that by merging in this way control and optimization, you get both the benefits of both sides. Of course, this block diagram is not uniquely to GIS. There are many historical ancestors and variations of it that have been proposed. Maybe a historical root is in process control in the name of, say, self-optimizing control or modify adaptation, where the purpose of solving sequential steady-state optimization problems was to reduce uncertainty in the system. The block diagram directly appears in extremum seeking, with a minor difference that the algorithms that we use in extreme seeking are derivative-free, so they only rely on function evaluation, but they're hard to implement and generalize when you have high dimensions and any sort of constraints. You can also think about what I've just shown you as a particular case of model predictive control, MPC, but of course without dynamic optimization in our case. On the other hand, we have MPC with anytime guarantees. That is, we have algorithms that we can stop at any point in time, such as real-time MPC or real-time iteration. So these are sort of conceptually related frameworks. More closely related is the literature on communication networks, when around the turn of the millennium, people like Kelly, Lowe, or Srikant realized that you can inversely model the Internet Congestion Protocol, TCP/IP, as an online optimization algorithm. And then, of course, you can improve upon that using different optimization and control methods. There's a lot of literature dating back quite some years on optimization algorithms as dynamical systems that has recently seen a revival in the context of the work by Laurent Lezin, Stephen Boyd, and Michael Jordan and their groups. And there's been also recent system theory approaches exploring this block diagram using output regulation and robust control methods. Very closely related, I want to tell you today, is the literature that came from the power system community or from people that were performing theoretic research, but inspired by power systems. Namely, the community realized very quickly that these open online optimization algorithms are great feedback controllers for power system applications. And that has sparked a whole lot of theoretic development. Okay, so here's a recent survey by Maltzen and others. Here's my personal clustering of research groups involved in the topic. I'll let you guess the clustering criterion. An early adoption of these algorithms was due to Jokic in the name of KKT control for the purpose of power system balancing. And around 2013, different groups in the US and Europe simultaneously started research on essentially distributed optimal integral controllers that would drive the power system to an optimal steady state. So early on, the focus has been on distributed algorithms, but rather simple models, whereas now the focus has shifted to centralized algorithms by more and more complex specification, complex methods, complex models. These algorithms have seen different implementations in lab-scale microgrids, but also in large-scale transmission systems. For instance, a weakly related concept is transactive control. So I would like to now explore this block diagram that I've just shown you today. In particular, what I'd like to understand today is, can we derive any sort of closed loop certificates, for instance, on stability or optimality? This will eventually lead us to studying projected gradient flows on manifolds. I want to discuss implementation aspects. And throughout the presentation, I will illustrate the theoretic developments with power system case studies. Let's get started. Let's take a look at a simple algorithm and an optimization problem. So here's the optimization problem. It's an objective function phi depending on two variables, y and u, and we will later associate y and u with the outputs and the inputs of a dynamical system. Certainly, outputs and inputs are related in steady state through the steady state map of the system. So you have y is equal to h of u for some function h. So this constraint is explicit. And you have constraints on this on u. Say u is in calligraphic u modeling, for instance, actuation constraints later on. I'm now looking at simple algorithms to solve the optimization problem and continuous time algorithms. Why continuous time? Because I want to later interface this algorithm with continuous time physics. Of course, we have to discretize, sample hold discretize algorithms in applications later. The simplest continuous time algorithm is a projected gradient flow. That is, as long as you're in the interior of your feasible set, this gray region, you just follow this vector field, which is the gradient of the objective. And whenever you hit a constraint surface, you slide along tangentially and eventually get to a local optimizer down here. So to formalize this very intuitive and simple picture, what you need is the notion of a projected dynamic system. So you don't have a differential equation x dot is equal to f of x, but now the vector field that is on the right-hand side of your differential equation is projected, and this projection pi is the following. It will see, we look for the closest vector v to f of x within some feasible set. What's the feasible set? If you look down here, what we look at this point is a set of all feasible admissible directions. So all directions that the vector field can take, where the solution can flow along, that will make you stay within the interior of that feasible set. Okay, so you find the closest feasible direction. And you do this also typically with respect to a certain non-constant metric. So the ingredients here, we have some domain X, okay, in which we have to live. We have a vector field, we have a metric, and we have a tangent comb, which tells us what are the feasible directions. All of these have to be sufficiently regular for a solution to exist, and I will discuss this later on. So now for the optimization side, what we look at is a projected gradient flow. So follow the gradient, already replaced here y by h of u. And we project on the feasible set whenever we encounter the boundary. When you appeal to the chain rule, you can write this here as a dh du, an identity. And here's the gradient of phi with respect to y and u. And then you have to do a point evaluation at y is equal to h of u at any point. And you wonder, why do I write this simple gradient flow in such a complicated way? The reason being, if you replace this point evaluation now by a measurement, so a measurement y from a dynamic system, then now you have an open algorithm that you can interface with the system. It turns out projected gradient flows will converge on a very weak assumption. So if you have a sufficiently regular solution, where regularity will be discussed later, this will converge to a set of critical points of the optimization problem, provided that your objective function has a Lipschitz gradient and compact sub-level sets. So very, very weak assumptions. Let us now interface such a projected gradient flow with the dynamic system. For now, let's stay within the simple world of LTI systems. So we have an LTI system with matrices A, B, C, and D. And we also include disturbances, EW and FW, on the process and the output. Let's assume this dynamical system admits a steady state. So probably we need some stability assumption. We need the disturbance to become asymptotically constant. Then this steady state can be written as follows. You can solve for x as minus A inverse BU and minus inverse EW. So this will be the map HIS from the input to the state. And this will map from the disturbance to the state. And same for the output, where HIO will be the steady state input-output map. And the same for the disturbance. We now want to formulate an optimization problem on the steady state of this dynamic system. So the optimization problem will be formulated on the sets of inputs and outputs that are related through the steady state map. And we have constraints U. So U has been a calligraphic U set. And now we'll use that simple projected gradient flow to drive us to an optimizer, with the difference being now that I use an open gradient flow. That is, instead of using a point evaluation, y is h of u, I replace this by a measurement. So here's the block diagram. I have here on the right-hand side my ABCD LTI system with disturbances. Here I have my projected gradient flow, and now I real-time interconnect the two. Okay. Another thing I highlighted here, I use a scaled gradient flow. So I give myself a gain epsilon here, if you want an optimization language, a step size. And the purpose of that gain is to reduce the input-output gain of this algorithm, or to enforce a timescale separation between these two systems. In particular, whenever you see an epsilon, you know it has to become small, right? So if epsilon is small, you enforce that the algorithm runs slower than the LTI dynamics. So when is this entire closed loop well posed, stable and convergent? We need the following assumptions. So we need that the gradient flow in isolation is well posed. So we have compact sublevel sets and a Lipschitz gradient, Lipschitz constant L. we need the LTI system to be asymptotically stable with convergence rate tau. That is, there exists a Lyapunov matrix that satisfies the Lyapunov equation, PA plus A transpose P is less equal to minus 2 tau P. And we need a sufficient timescale separation. If you want some sort of small gain separation between the two systems, that is, our epsilon should be small. It should be smaller than some value epsilon star, which depends, if you want, on the convergence rate and input-output gains of here the algorithm and here the LTI system. So it's 2 times the exponential decay rate scaled by the condition number of the Lyapunov matrix. Under these assumptions, you get that the closed loop system is not only stable, it will also globally, from any initial condition, converge to the critical points of the optimization problem while remaining feasible at all times. Because at all times you stay in the interior of the domain you optimize over and you will converge to critical points. So it's a very powerful statement under, I would say, rather weak assumption. And what's very nice about this, the proof is very simple and robust. Namely, for the proof, we rely on a Lassalle-Lyapunov argument that has been proposed by Saberi and Khalil in '84, which again relies on a single perturbation theory. In particular, what we use a different set of coordinates. So in single perturbation theory, this coordinate would be called the boundary layer error coordinate. What is it? It's a difference between x minus its steady state. So if you want, so it's the steady state error of the state. And now we find a separable Lyapunov function in these new coordinates. So here's the Lyapunov function of the LTI system in this new error coordinate. And here's the Lyapunov function of the algorithm, if the algorithm was in isolation, so you replaced y by h of u. And now I just take a convex combination of these two terms. So I found a separable Lyapunov function where delta is in 0, 1. Now, with some attention to details, conceptually the proof is very simple. You just check the derivative that function is non-increasing, which turns to be true if epsilon is less than epsilon star, which is this value, provided you've chosen a good value of delta. Okay, so quintessence of the proof, in these new error coordinates, you can find the separable Lyapunov function, which is decaying under sufficient timescale separation. So it's a very simple proof, and you can already see this can be extended to much more general setups. Before going there, let me illustrate this theorem to you with an example. So appealing again to the Pauston balance example, let's see if we can do this now in an optimal way. Can we do optimal frequency control? So what we can control are the generation set points of an LTI power system model. What we do not know are any sort of disturbances by loads or renewable generation. What we measure is system frequency, as well as all variables we'd like to constrain, for instance, injections and line flows. The details of the power system are here. I will not discuss them. Essentially, we stay within the assumption of theorem for now, so we use LTI dynamics. Our optimization problem has an objective to minimize the cost of generation while sort of driving the frequency to its nominal value. And we incorporate our operational constraints on line flows and frequency here as soft constraints in the objective. Later on, we'll do more sophisticated things than soft constraints, but for now, I'll stay within the assumptions of the theorem. We have explicit constraint in the actuation that we will project on using projected gradient flow. And of course, we have the steady state map from the input and the disturbance to the output. The control at the end is just this projected dynamical system. So follow the gradient and project on the tangent cones at the constraints. So if you want, this essentially is an integral control or a supercharged automatic generation control in Pauston language. What is this doing for you? Let's look at an example, the IEEE 118 system. Initially, we are not yet at the steady state solution or optimal solution. So initially, there will be a transient where we converge to this dashed line. What I show here is the generation cost. So we very quickly converge to a globally optimal solution. So that would be the ground truth optimization if we were to solve the optimization problem at every instance in time. We do so despite the system undergoing some events, some contingencies like a generator outage or a double line tripping. And frequencies will be nicely stabilized despite these disturbances, so we gracefully ride through them. Here are the variables that we project on, so the generation costs, so notice we satisfy the constraints at all times. And here are the constraints we incorporate, for instance, using soft penalty method. And you see we also nicely satisfy the constraints here. Okay, so the transient curves look very nice. Let's look at the assumption of our theorem. The main assumption was we enforce a timescale separation between our algorithm and the dynamic system. So we had epsilon less than epsilon star, and now let's ask how conservative is this assumption. If you move away from the sufficient conditions, so you double epsilon, you see things still work out, though it's getting increasingly unstable in terms of the transient excursions become larger. And if you go away by a factor 10 from the sufficient condition, you see an instability. So we conclude here that our condition for this particular case study is, it's not exact, but it's also not conservative. It's within a factor 10. Of course, this conservatism depends very much on the problem, how you choose your penalty scalings, and so on. So just a small wrap up of what did we learn from the simple example and the LTI system analysis. We don't need a whole lot of assumptions in the plant. We only need internal stability, no observability, no controllability. We could arrive at a similar type of certificates if the plant had more structure, passivity, or some sort of primal dual structure, but in general, we don't need this. We need very little model information, so we only need measurements in a steady state input-output map. In particular, we don't need the dynamic model, we don't need the state, and we don't need the disturbances. Okay, we converge to optimality or local optimality no matter what. We have very weak assumptions on our optimization problem. We only need a Lipschitz gradient and compact sublevel sets. We don't need convexity. Of course, having convexity gives you the global optimality, but in general, it's not needed for the proof. So the problem setup is very simple, very parsimonious. Potentially you get a conservative bound, but you have minimal assumptions on the plant and on the optimization problem. And the proof is very simple and robust. That is, you can easily extend it now to your favorite class of nonlinear systems, to time-varying disturbance and more general algorithms, of course under some assumptions which I'll discuss later. So the takeaway is that these online open optimization algorithms work very well as feedback controllers. Okay, and this will be our working hypothesis for the remainder of the talk. Let's go a little bit more general towards nonlinear systems and general algorithms. So if you have a nonlinear vector field, f of x and u, you need to assume that there's a steady state of the system, and you can apply an implicit function theorem to the steady state. So locally, you can find a function x as a function of u, so x equal to h of u. This will be your input to state map. You need to assume that this system is incrementally asymptotically stable, incrementally with respect to this steady state error coordinate. Okay, so your Lyapunov function will formulate as a function of this error. In particular, your Lyapunov decay will be quadratic in this error, and your growth rate of the Lyapunov function in u will be linear in this error with some constant theta and gamma. So this is the assumption you need on the plant, essentially incremental asymptotic stability. On the algorithms, let's go slightly more general. Let's not use a gradient flow, but let's use a variable metric gradient flow, where I throw in front of the gradient here a matrix Q of U inverse. So this matrix is state dependent, but I assume it to be positive definite for all inputs U. It looks very esoteric. For those who are familiar with optimization, you will recognize this as being when an instance, for instance, of the Newton method. If you were to choose the Q of U, the metric, to be the Hessian of your objective, you get the Newton method. You can also use more exotic maps, for instance, to get the mirror descent. What does now the stability condition look like? It's very much the same as before. Something has to be small, less than 1. In particular, it's the same as the previous condition. We replaced the epsilon now by the worst case value of this metric. And the convergence rate of the system will be, in the nonlinear case, the growth rate zeta divided by the Lyapunov k gamma, and here you have the Lipschitz constant of the algorithm. So it's very much the analogous condition. You can now also go to other algorithms, for instance, algorithms that have memory states, such as momentum methods like the heavy ball, or primal dual methods, as long as you can satisfy some sort of exponential stability, or your favorite combination of weighted metrics, memory states, and projections. It turns out for all of these algorithms, the proof is very much the same as in the previous LTI example, and you always get to such a stability condition. And I want to stress that the assumptions you make are rather tight. That is, you need a bounded metric and a bounded Lipschitz constant. And let me illustrate that you have some non-examples. For instance, the discontinuous subgradient flow does not have a bounded Lipschitz constant, or the Nesterov acceleration does not have a bounded metric. Both of these work fine as offline algorithms, applied to an algebraic plan. But when you interface them to the dynamical system, these algorithms will actually not converge because they don't have a bounded metric or a bounded Lipschitz constant. Okay? So you cannot take any optimization algorithm. There needs to be some minimal assumptions. Let me show you what we can do with this. I want to explore a highly nonlinear test case. In particular, what I'd like to understand is now voltage collapse in power system. A voltage collapse is a phenomena where a sequence of events drives the system to a point where it undergoes a settle node bifurcation. That is, two equilibria merge and disappear. It's a highly nonlinear scenario. I'm currently on a sabbatical in Sweden, and I thought it's appropriate to use an example from Sweden. So this voltage collapse occurred in southern Sweden in '83. It's a famous historical event. And so what I use now is an example of the Swedish system modeled in gory detail. So here's some details on the modeling. And I'll like to understand this voltage collapse and how we can mitigate it. So here you see the curves of voltages at different nodes in the system. So generation, transmission, and distribution buses. I have an event that is between 500 and 800 seconds. I increase the load very lightly, not by much, 250 megawatt. And first you don't see anything, and then the voltages all fall down, hence the name voltage collapse. What's happening is that a bunch of decentralized controls in the power system react to this increase in load in a very unfortunate way. Namely, it's decentralized controls that are not coordinated and that eventually will reach a saturation and cannot respond anymore, and then everything goes downhill, literally. So it's very hard to mitigate the settle node bifurcation of voltage collapse via conventional power system controls. So let's see what our online optimization can do. In particular, let's assume we have access to the generation set points, to the set points of the automatic voltage controls of the generators, and apply feedback optimization to update these set points. The cost function we pick will be a cost function related to settle node bifurcation. So something becomes singular, some equilibria disappear. So we put here essentially is a cost that makes sure that something does not become singular. A particular matrix, namely the power flow Jacobian, should remain regular. And so I put as a cost minus the log determinant of that matrix. And you can see that even in this highly nonlinear case study, this type of feedback optimization can avert the voltage collapse. So this is just to show you how much confidence we actually have in these algorithms, and we can apply them to very nonlinear large-scale systems and case studies. Let's move on. I think I've convinced you now that under sufficient timescale separation, you can apply these algorithms to a dynamical system. And thus, what really remains to be studied is how do these algorithms work when we interface them with the steady state of the system. Okay? And the steady state of a dynamic system, at least for a physical system, typically has some sort of smoothness properties and takes form a manifold. So let's understand these algorithms when they flow on manifolds, particularly the projected gradient flow. Let me again motivate this from the viewpoint of power systems. So I'll now go a little bit in details, but not beyond high school physics. So we need three equations: Ohm's law, voltage is impedance times current, Kirchhoff's current law, sum of all currents is zero, and AC power says the product of voltage and current is power. Okay. If you combine these three equations, you get these complex valued quadratic equation, which give you the balance of complex power at every node. You can split this, of course, up into real equations for the real and imaginary part called active power and reactive power. Conceptually, very simple equations, just quadratic equations. But for all of you familiar with quadratic equations, you know they can be rather complicated. In particular, you can look at a simple low-dimensional three-node power system and plot the solution surface of these quadratic equations. And it looks rather complicated, even for such a small system, definitely non-convex and non-linear. What saves you at the end of the day is typically operating somewhere on the upper end of this surface, which is not as non-linear, it's rather flat. But now imagine putting operational constraint in the system, which will eventually slice this surface, okay? And it will become even more non-linear and possibly disconnected. Here's another famous example by Dan Maltzahn from 2016, where he had, I think, a 5-bus power grid, and this would be the solution surface here. Most algorithms will drive you to this point here, which is a local optimizer, but the global optimizer, so when you slice with this constraint, is another component of the feasible set, so it's disconnected, which is over here, and so you can have these disconnected feasible sets even. On top of that, you typically have a lot of parameter uncertainty, up to 20% in these equations, And you should think of this really being only the steady state of a highly nonlinear dynamical system. So all of this makes power system interesting. So where's the manifold appearing? So some of the good news are that these power flow equations are complex, but you can formally show that they take the form of a differentiable submanifold. Okay, so it will be nice, well posed. You can attach local tangent planes everywhere as approximations. It turns out you can then locally invert the equations on this manifold. Also, constraint satisfaction conditions like LSAQ will hold generically on the surface. So you have a lot of regularity. Essentially, everything will be differentiable, derivatives will be full rank, and you can take inverses, which gives you flexibility for the algorithms. Also notice that this manifold is the steady state of an ambient dynamic system, and it's a locally stable steady state. That is, the physics of a power system will eventually drive you to that manifold, so they enforce feasibility even when the algorithm performs non-exact steps, which gives you a lot of robustness in terms of the algorithm, but also when applied in closed loop. Good. So now let's apply feedback optimization on this power flow manifold. So the physical system now is just modeled in steady state, so this power flow equations. On top of this, of course, you have uncertainty in the form of unknown injections of load and renewables. So the left-hand side, you have an additional injection here. And you have these gradient equations, and we interface now in real time for projected gradient flow. And what are these objective and constraints? So the objective will be something like minimize losses or cost of generation. On the constraint side, you have to be on the AC power flow manifold. So these are the gradient equations. And you have operational constraints, typically taken from box constraints, limiting the generation. So let me draw again a picture from another low-dimensional example. So power system scientists will recognize this as a projection of the so-called nose curve. So it's a curve in the power voltage domain. And here you see this power flow manifold, this orange surface. We slice it with constraints on generation and voltages. And what our algorithm has to do, we have to slide along the surface to a constraint optimizer. That is, we have to stay on the manifold all times. So we need to project our descent direction on the tangent plane. Wherever we go, we also have to remain feasible. So we also have to project inside the feasible cone using the projected dynamic systems framework. And finally, this has to be a descent direction we get, so we converge to a local optimizer, or possibly even to a global optimizer. And now you wonder, well, all nice and fine, but people work on power system without all of these specifications. Often they just linearize things. Is this level of generality really needed? Is this just technical sophistication? Let's look at some simple low-dimensional case studies. So for this simple system, that would be the power flow manifold. This is the feasible set within the constraints. So you start from here, the algorithm drives you to the constraint, you slide along, you get to global optimizer. Yes, it is a nonlinear manifold, but it doesn't look as dramatic as the previous picture. Presumably linearization works well. Fine, that's granted. Here's another even simpler case study, only 3 buses. Here's the manifold again, in particular projection. And this black line would be then the feasible set in that projection, and it looks definitely very nonlinear, non-convex, and even non-smooth. And so the takeaway is that the application, even for simple case studies, demands a rather sophisticated level of generality. So let us understand when a projected gradient flow on such highly irregular domains will actually converge to an optimal solution, locally optimal solution. So what we have to study is now a projected dynamical system, okay, where we have the gradient of an objective, okay, and we project on the tangent of the constraints with respect to some metric. And what we'd like to understand, does this converge or not? And what does it converge to? And it turns out when you have a solution to these equations, and if your objective function has compact sub-level sets on the feasible set X, then X of t will converge the set of critical points of your cost function on X. Okay, so essentially under almost no assumption this will converge. The devil's in details, namely assume you have a solution, particularly you have a Kara-Theodori solution, so an absolutely continuous function that satisfies this differential equation almost everywhere. Solution exists for all time, and it's viable, it's within the feasible set, and you have an equality sign, so there's some notion of uniqueness. Okay, so we have to understand when this is the case. Before that, let me show an example. So here's the manifold is the ball, so x squares 1, and we slice the ball with a diamond, and we have here a flow on the set where we project whenever we hit a constraint, and we can actually certify this flow will converge nicely. Okay, and this, is fairly non-trivial. So the devil's in details, namely, we assume we have a solution. So the hidden assumption is, when does the solution exist? When is it unique? When is it viable? When is it complete? When you don't have Euclidean space, you don't have convexity, you don't have standard metrics, and so on. And that's where a lot of our work goes into, and we have to dig a little bit deeper and find the regularity assumptions when this is the case. For instance, we have existence of such Carathéodory solution, provided our constraint set is Clark regular, so we don't have any inward cusps. The vector field is continuous, the metric is continuous, the manifold is differentiable. And uniqueness we get essentially when vector field is Lipschitz, the metric is Lipschitz, the manifold is Lipschitz differentiable, and the constraint set is proximally regular, that is, it admits locally unique projections. It turns out for the typical Poisson optimization problem, this will always be the case, essentially thanks to the nature of the manifold, which certifies that you will have full rank Jacobians. But you can, of course, construct examples where it is not the case, and you can actually find out that these sort of assumptions are minimal. That is, you can construct counterexamples whenever you remove any of these assumptions here. Okay, so you understand you have to do some deep math or deeper math, go into variational geometry to understand these projectional dynamical systems. But then you also want to implement those. And when you implement them, you have to take other effects to account. In particular, the first thing we realize, if you want to implement a project dynamical system as a feedback control, two ingredients will be a projection integrator, which is a recipe for wind-up, bang-bang type behavior. So to remedy that, you probably need an anti-wind-up approximation that robustifies you. So for instance, if your feedback control is of the form k, a function of x and u, and you want to project this vector field, u dot is equal to k, a robust way to do this is just do a pointwise projection on the output, compare this pointwise projection to the u, and feed this back negatively with a high gain. So this is essentially an anti-wind-up approximation. What is nice that this saturation often comes for free by the physics of the plant. You can actually formally show, Adrian has done that in a sort of mini sabbatical in Santa Barbara of NDTL, that this type of robust anti-wind approximation converges in the sense of graphical convergence to your projected dynamical system. So this is how we would implement this robustly. Also, you'll be subject to disturbances, not only smooth and continuous disturbance, but disturbances that may change your domain. So your x of t, where you project on, will be time varying. And so you have to understand what is the temporal tangent point to project on, when is all of this well posed, and how to derive some sort of tracking certificates, that is, under what case of changes. For instance, if the change of the domain is Lipschitz continuous, will you still track an optimal solution, and with what error? Further on the topic of uncertainty, so when you have input constraints, you can robustly deal with them by using this anti-wind-up approximation projection. But what about non-input constraints, when you have constraints in the state or the output of the system? So state constraints, clearly we cannot measure the state, so we have to estimate it with, for instance, a Kalman filter. And in some assumption, you can also derive a separation principle between the algorithm, the system, and the Kalman filter. What about then how to enforce constraints? For instance, the case of output constraints, you cannot enforce them by projection or any sort of some sort of anti-wind-up projection because this is not an actuated variable, right? So this cannot be done. Also, you don't necessarily, you can measure the output, but typically what you don't have available is the functional form, how is y related to h of u. Typically, this will be uncertain and you have disturbances. The way people deal with that normally in feedback optimization is to either incorporate the constraints as a soft penalty or to dualize them and then use an appropriate gradient or saddle flow. This sort of works okay-ish, but it's a little bit hackish also in terms of it's inaccurate. At best, you get asymptotic feasibility and typically need strong assumptions when this will actually be well posed. What we found works better is an SQP style method where what you do, you approximate your output map, y is h of u, by a first order prediction. So you say y is equal to the measured variable. And then, of course, you will go somewhere using a gradient descent map. So where you will go, you approximate using a first order approximation, which requires you to know the sensitivity, the dHdu, which you need to know anyways for your projected gradient feedback. And then you have a feasible descent direction. And now what you do when you search for the feasible descent direction, you project on this approximated constraint. And you can actually certify that this will also get you globally to the set of critical points of the optimization problem, even in the absence of convexity, linearity, and so on. Let's see how all of this works out in a non-trivial example. So you have another power system. Everything will be now time varying with a lot of disturbances. So here's the net profile of the aggregated load and renewable generation, solar and wind, which is, as you can see, quite time varying and even discontinuous at this point where a load is turned on and off. The algorithm we run is a projected gradient flow feedback control, subject to all of the modifications I've shown on the previous slide. You can see when you look at the transient curves that all the variables you're interested in stay nicely within the constraints. So you satisfy constraints actually at all times. And some of these constraints are time varying even, and you'll satisfy those. For instance, the purple curve is the solar generation, which is time varying throughout the day, of course. You see here, you don't use all of the solar power. You actually curtail, reason being otherwise you would violate some voltage constraints. So takeaway is that you have transient trajectory feasibility despite disturbance uncertainty. If you compare the solution to the ground truth optimizer, which is omniscient and has no computational delay, what you see actually nicely track the ground truth optimal solution, despite all this discontinuous nature of loads and renewables. So it works out very nicely. So you track ground truth. And moreover, this is a very robust model mismatch. That is, if you perturb your model quite severely, say you perturb the loads by 40%, your algorithm does not know that, but you will still be feasible. You will actually converge to global optimality, despite having a severe mismatch in parameters here. If you think back, you can think about load perturbation as an additive affine disturbance. And we proved before for the LTI case that you don't need to know the affine disturbances, right? And so maybe it's not surprising to get to optimality here. You can also throw in more severe disturbance if you want, so multiplicative disturbance, so you don't know the line parameters. So if line failures, you'll still always be feasible and get very close to optimality. In comparison, an offline optimization method, which in this case was not aware of any of the model uncertainty, would get nowhere close optimality and would probably most likely not even be feasible. Okay, and so we get all of this uncertainty essentially due to feedback, due to forgiving nature of feedback. So we conclude that this rather simple algorithms perform extremely well and are very robust. Before concluding, I just want to show you some experiments when we apply this to a real system. So we ran some experiments at a microgrid DTU where we can sort of build our favorite type of power system. The details for now are not so important. Let me jump over details due to time constraints. Essentially, are some baseline controls which take the form of some linear or piecewise linear feedback controls if that's on saturation effects. And we now want to compare what happens with the baseline decentralized controls, the feed-forward optimization, and the feedback optimization. We see for the decentralized feedback control that once we turn the controller on, it is not able to make sure that the voltages stay within constraints. Why? The battery reacts as good as it can, but it reaches here saturation and is not able to stabilize this signal into the feasible set. The reason essentially is we have local control saturation and the controllers are not coordinated. So we need some sort of coordination to avoid this effect. If we use successive feed-forward optimization, which would have access to a centralized model, omniscient, and is successfully updated at a high sampling rate, you can make these curves jump very quickly from one set point to another, but it turns out you still have a steady state mismatch. The reason is that you still have parameter uncertainty. Even in this microgrid where you know everything, you have enough model uncertainty to not end up in the feasible set. And this is what feedback is good for. Let's run our feedback optimization in real time. And you see you very nicely make sure all the variables go within the feasible set. Despite the battery being saturated, you stay within the feasible domain. I should say we used a very low sampling rate, so every 10 seconds we essentially take a gradient step, and nevertheless this nicely converges. So we have excellent performance. Notice to implement these controllers at the end, the only piece of model information we need is the input-output sensitivity, so gradient h of u. It turns out here we only used an estimate, namely we knew by physics that the gradient h of u is a non-negative matrix, of course depending on a lot of parameters and states, but we just approximated by the matrix of all the ones, and nevertheless it would work out very nicely. So in this case, even a completely model-free method. Let me jump to the end. In conclusion, what I hope to convince you of that we can use this open and online optimization algorithms as feedback controllers. Our approach relied on projected dynamical systems and timescale separation. I showed you a unified framework that encompasses a broad class of systems, algorithms, and programs, and I used past and case studies to illustrate all of the developments. As part of our ongoing work, we want to understand more in detail some robustness issues, performance, what happens when you throw in stochasticity into the system, so analysis questions. On the algorithmic side, we'll be interested in gradient-free algorithms, estimate sensitivity online, see when we can distribute these algorithms or solve them robustly. For the Power case study, we see that these algorithms work very well, but I think we need more experiments and more case studies to really test when do they break down and further refine them. Finally, I think there's some further applications beyond power system communication networks where these type of feedback optimization algorithms would be really useful, essentially whenever you have highly uncertain and constrained plans where you seek optimality. For me, a personal takeaway is that these methods work really well, surprisingly well, maybe much better than they should, and we still need to fully grasp why. Now, I thank you very much for your attention.